I'm Jeffrey Zalc. Here's a brief bio, but basically I teach part-time at Illinois Tech. I teach chemical process design and chemical process simulation, and I work full-time in BP Solutions in Naperville, and I've been doing chemical process modeling there for almost 16 years at this point.
Hi, Jeff.
Hi. How are you?
Very good.
Awesome. You can.
Hello, students. My name is Professor Shimilewski. I teach with Professor Zalc. Oh, there we go. That's what I was going to tell you, Jeff. You need to go to full screen because your other one wasn't.
Okay, that looks okay.
That looks much better.
Okay, so Juan, like I said, I work in BP Solutions. I work in the process modeling space.
Hi.
And I wanted to just give an overview of kind of what type of work I actually do and what it entails. So if you can think of petroleum refineries and chemical plants as consisting of many different pieces of equipment, right? These pieces of equipment are called unit operations. So a unit operation is a piece of equipment that's used to change something about a fluid material in a chemical plant or a refinery. So unit operations can change the chemical composition, the temperature, the pressure, the phase conditions, etc., of streams. And a stream can consist of many different types of molecules. You might have a stream that's just liquid water. You might have a stream that's liquid benzene. But if you're dealing with, for instance, a petroleum refinery, you can have different types of streams that are portions of, effectively, of an oil barrel. And each stream can consist of many, many, many molecular types. So you could have essentially infinite number of molecular types, ranging from light molecules like hydrogen and methane and ethane and propane, all the way up to molecules that have tens of carbon atoms in them. Now, the unit operations in a chemical plant or a refinery will include things like chemical reactors that are used to convert feedstocks into saleable products, heat exchangers that are used to either add or remove heat from streams to change their temperature or their phase conditions, distillation columns that are used to separate different molecules based on their differences in boiling points, and then pumps that increase pressures of liquids, compressors that increase pressures of vapor. You have valves that reduce pressure. You have all kinds of other different pieces of equipment. And for every type of unit operation you can think of, there are chemistry and physics laws that describe what happens in each unit operation. So things that apply to a given unit operation could include, material, energy, and momentum conservation, right? If I have a chemical reactor, if I'm flowing 10 pounds per second of feed into it, 10 pounds per second has to come out of that reactor, because unless we're having nuclear reactions occur, the amount of mass going in has to equal the mass coming out. The types of molecules can be different, but mass has to be conserved. You also have to make sure the energy is conserved and momentum. You also have equations for things like chemical reaction rates, thermodynamic equilibrium, which will dictate how much a reaction can occur or what kind of phase conditions will exist in equilibrium with each other. So if you think of these chemical and physical laws as a very simple example, I could look at a ballistic trajectory. So I could have a ball that's launched at some velocity and from some position, and I can write down on the right side here the equations that describe its motion. So I can mathematically determine how long that ball will be in flight, how far it's going to land from the point at which it was launched, and the maximum height of the trajectory. So just like I could solve these physics equations to describe the trajectory of a simple ball that's thrust into the air, there are many, many, many equations that I would need to solve for a given unit operation in a chemical plant or refinery in order to describe the behavior within it. So the equations that describe the behavior within a given unit operation are called governing equations. And unlike the case of this ballistic trajectory where I can write down the equations and I can solve them by hand, the equations that relate to a unit operation in a chemical plant or refinery will be numerous, and the equations will be very complex. You couldn't sit down and solve them by hand. It would either be impossible or it would take basically forever. So the equations will get solved numerically on a computer using software that's called a chemical process simulator. Any questions so far, Juan? Okay, so I have a picture of a refinery here. This is our Whiting refinery in Indiana, and we have heat exchangers that are these horizontal cylinders. We have distillation columns that are the vertical cylinders here, and there's all kinds of piping and different pieces of equipment there. And if, in order to safely and profitably and efficiently run the refinery, it's necessary to understand how each of these pieces of equipment will behave and how the whole plant will behave as a whole. So a chemical process simulator allows us to basically make a detailed equipment-based model of a chemical processing unit or of an entire refinery or chemical plant in order to understand it. So the simulations that we do, they can be used to determine what types and what qualities of products are going to be made based on certain operating conditions, such as temperatures, pressures, flow rates, reactor configurations, etc., and for a given type of feed. And then we can make predictions based on simulations to determine, well, when will I need to clean this piece of equipment or perform maintenance on it? Is it going to last another month? Is it going to last another year? Is it going to get fouled or have problems next week? So you can use simulations to understand the ongoing operation of a piece of equipment or a chemical plant. You can make predictions to understand when you're going to have to clean or maintain different pieces of equipment. And you can use these simulations to figure out how to maximize the profitability, to minimize the emissions, etc., in order to run the plant safely and how you want to. So this picture just on this screenshot shows a flow sheet simulation that I had made, and this is a process model for what's called a catalytic reformer, which basically takes streams that would get blended into gasoline that you would buy at the pump, and the reactor here in the center of the screen basically contains materials that help convert that gasoline material to have higher octane, right? Because you buy octane of 91 or 93 or 87 octane, and this reactor helps increase the octane and thus increase the value of the material. So a process model involves constructing a detailed equipment-based model. So each piece of equipment on my flow sheet is a piece of equipment in the field. I have a heat exchanger here. I have a reactor. I have a separation drum. I have a recycle gas compressor. I have a distillation column. So each of these pieces of equipment on my flow sheet corresponds to a unit operation that exists in the actual refinery. And when I run the simulation, I can tell the software, okay, well, how much and what type of feeds am I sending in on the left side of the screen? How is my reactor configured? What does my heat exchanger look like in terms of size and conditions, etc.? How big is my distillation column? And I can enter all of that information into the simulation, and it can solve all of the governing equations for all the different pieces of equipment, and it can tell me things that would either be difficult to measure in practice or impossible to measure, or I can use the simulation to basically do experiments to determine, well, what's the best way to run this equipment next week or next month? If I get a different type of feed next week, what's going to happen? Am I going to be able to operate as well as I was last week, or am I going to have to change something about how I'm operating? So I'll go live for a moment here. This is the actual software. It's called PetroSim. There are other competitors called AIChE and Pro2, etc. But doing this kind of simulation is a very common thing that chemical engineers will do in chemical plants and refineries. So I can, for instance, look here, I can double click on this report, which tells me different properties of this gasoline stream. And I can see here that, for instance, I have a 100.01 octane number, okay? And that is the result of all of the calculations related to all of the upstream operations here. And by the time I get to this gasoline blending component, I see that I have a 100 octane. Now I can say, well, what happens if tomorrow I'm going to be asked to process 10% more feed? So right now, say I have 29, suppose I have 3,000 barrels per day going into this unit. I have an octane of 99.93. My boss may ask me, okay, well, what happens if we try to process 10% more next week? What's going to happen to my octane? Is it going to go up or is it going to go down? Well, I suspect it's going to go down because I'm putting more material through my reactor that it has to process. So I'm probably not going to increase the octane as much as I'm doing in this case. But the question is, how much will the octane drop? And that's where the model can tell me things that I wouldn't be able to know otherwise. So I can say I'm starting with my initial case with 3,000 barrels per day. I have a 99.93 octane, and I can say, suppose next week I increase my throughput by 10% to 3,300 barrels per day. Then my octane goes from 99.93 down to 99.72. Okay, so it went down by a fifth of an octane number, and then the question becomes, is that acceptable or is that unacceptable? And if it's unacceptable, but I still have to process this extra 300 barrels per day, then I can use the model to understand, well, what can I change to try to get back to my 99.93 octane if I still need to process this higher throughput? So I can say, well, maybe if I come into my reactor, if I run my reactor a little bit hotter, maybe that will help because I'll get more reactions occurring. So instead of running at 911 degrees Fahrenheit, let me see what happens if I go to 915 degrees. I can increase the temperature. I could look what happens to my octane. Okay, it went up a bit, but I didn't get back to where I was. Let me go to 920. I'm up to 99.84. Let me go to 925. And I'm at 99.92. So the implication would be if I need to operate my unit with 10% more feed next week, then my guidance to the operations people would be that, well, you're going to need to increase your inlet temperature to the reactor to 925 degrees in order to keep approximately the same octane level as we have now. And I could have done that. There are tools in the software to automatically adjust the temperature to hit a desired result. I just kind of did the exercise by hand to show you kind of what the procedure is. So any questions about that, Juan? Or
could you hear me?
Yeah, does that make sense? Or is there anything you want to ask?
Could the refineries overheat and explode, or like?
So yes, I mean there are, operating safely is top priority, but obviously if you watch the news, there are instances where chemical plants and refineries have accidents, there are explosions, and there are fires. So each piece of equipment would basically have a set of design operating limits. So I may have a reactor that's only supposed to operate up to some temperature. It might be 950 degrees F, might be 500 F, but each piece of equipment based on the thickness of the materials that constitute it, the type of metals, the type of materials that you're processing, you'll have different allowances for how much material you're able to process at what temperatures and what pressures. And obviously, if you do have something that goes wrong and operating conditions deviate, you could have fires and explosions. But there are a lot of safety systems kind of built in to try to avoid that. And there are board operations people who would be able to sit in a control room and change some of the operating parameters related to pumps and furnaces and compressors and things like that, so that if they see an upset to the process, they try to get it back into a safe operating regime.
Yeah, I understand now. Thank you.
And we also, in terms of operations and safety, we use these types of simulations. So this is a steady state simulation. This is saying, this is a snapshot of how this part of the refinery will operate under these conditions. Now it's possible to make a dynamic model so that you can say, okay, well, if I change my feed rate, what's going to be the time evolution of this system, right? If I change my feed rate, my output is not going to change instantly. It's going to take seconds or minutes or hours for the material to go through all of this equipment. And you can basically make a dynamic simulation that tells you how the system behaves with respect to time. And you can essentially make something called an operator training simulator that allows people to respond to essentially fake incidents. So you can use the operator training simulator to say, well, what would happen if this pump died? What would happen? Well, I would not be pulling liquid out of this vessel as much, so it might fill up with liquid, and then I might send liquid into my compressor, which would cause it to fail. So you can basically use this operator training simulator, which is a type of glorified kind of video game, and you can say, okay, if this piece of equipment fails, what can I do to try to counteract that, to either bring the rest of the process back into normal operation, or what can I do to shut this whole part of the refinery down as quickly as possible to avoid an accident? So, I mean, if you're interested in engineering, if you become a chemical engineer, you'll likely end up using this type of software. I've had students at Illinois Tech who did this type of work for classwork and loved it, and went to work for the software company that makes this type of software. But within BP, we have maybe, on the order of 100 different types of models like this to simulate different parts of all of our refineries. And you can actually make a gigantic model that represents an entire refinery and involves, this is a refinery-wide model. So this is for our Whiting refinery. So each of these boxes, the gray boxes that says flow sheet, each of those boxes consists of dozens of pieces of equipment. And all of these blue lines represent piping of material in the refinery. So this simulation has thousands of streams and many hundreds of unit operations, and it is used to model the entire refinery. So then you can understand how to optimize it and how to invest, how to make capital investments. So you say, well, if I had $200 million to spend to improve the profitability of this refinery, where would I invest that money? Would I build another coker? Would I build a bigger ISOM unit? What would I do? And you can use the simulation to answer those types of questions to see where would be the biggest impact on making something bigger or adding some new piece of equipment.